Hello students, in today's session we are going to discuss design of eccentric loading. What is meant by the eccentric loading? So eccentric load is nothing but the load acting having some distance from the neutral axis of the component. So eccentric loading components are subject means how to design that component when these are subjected to the eccentric loading, that we are going to discuss today. So let us start with some numericals. Here is the problem statement. The frame of hacksaw is shown in figure. Here is the figure. The hacksaw frame is there. The initial tension in the blade should be 300 Newton. Here you can see the initial tension is to be provided to the blade on the hacksaw. So that initial tension must be 300 Newton. The frame is made up of plain carbon steel 30C8, that is designation of plain carbon steel, with tensile yield strength 400 Newton per mm square. This frame is made up of the plain carbon steel having SYT 400 Newton per mm square. The factor of safety is 2.5. The cross section of the frame is rectangular with ratio to depth to width is 3. Here in this diagram you can see this is nothing but the width and this is nothing but the thickness. So ratio of that width to thickness is 3. So if the thickness is t, small t, then width should be 3 times t, that is shown in this diagram. So we have to determine the dimension of cross section. We have to dimension of cross section means about this xx point. Suppose I took the cross section of that frame, then it look like this, and I have to find out the dimensions t of that C frame, that is hacksaw frame. So here is nothing but simple given data. P is nothing but 300 Newton. SYT is 400 Newton per mm square, that is material strength. Factor of safety for this frame is 2.5, and depth to width ratio is given, that is 3. So based on that dimension or based on that given data, we have to find out the dimension. Other dimension is also given, that 200, the distance of that force from this frame neutral axis or frame cross section we can say. So that is nothing but the eccentric loading. How the eccentric load is there? Here is nothing but the cross section of the frame, or this is component, and the load is acting from that cross section up to the distance of 200 mm, right? So that's why it is nothing but the eccentric loading. So axis of this is nothing but this one axis of component, and the load is acting at a distance of 200 from this neutral axis. So that is what the eccentric loading statement. So let us proceed for the solution. So in this solution, step number 1 is to calculation of permissible stresses. So in every design process, we need to find out permissible stresses first. So how to find out permissible stresses? Permissible stress, tensile stress is nothing but SYT divided by factor of safety. That is fundamental equation. As SYT is given 400 and factor of safety is 2.5. So allowable tensile stress is nothing but 400 by 2.5, that is 160 Newton per mm square. After calculating the permissible stresses, we have to find out what are the types of stresses that can be developed on the component. So component is nothing but this one. At this cross section, we have to identify the type of stresses will be developed. So in that diagram, from this diagram, we can conclude that the load is acting here. Due to that, this cross section will be subjected to the compressive stress as well as bending stress here. The compressive stress, because these two ends of frame are getting compressed due to that initial tensioning of the blade. So this component at this cross section XX will be subjected to the compressive as well as bending stress. So we have to find out this compressive as well as bending stress. How to find out bending stress and compressive stress? Well, we will see one by one. So compressive stress is simple force divided by area. Force is given, known to us, that is P is nothing but initial tightening force P divided by area of cross section of this one at section XX. So area of cross section is, by this diagram we can see 3T multiplied by T, as it is a rectangular cross section. So force per unit area. So by putting all the values here, we know the P is the initial tightening force should be 300, and area is nothing but T into 3 times T. So it becomes 100 divided by T square. Here in this equation, you can see that T is unknown, and that is to be calculated at the end. So the T will remain as it is in this sigma C equation. Let us say equation number 1. So after calculating that direct compressive stress, we have to find out the bending stress also. As this is force acting at the ends here, and that force transmit to the ends, so this frame will be subjected to the bending stress also. So how to find out bending stress? Here you can see the bending stress equation is nothing but this one, mby upon I, where mb is nothing but bending moment acting at this cross section, y is nothing but farthest distance from the neutral axis of cross section here, here nothing but neutral axis, and I is nothing but area moment of inertia. That is for rectangular cross section we need to calculate. So first we will concentrate on bending moment. How to calculate bending moment? Bending moment is nothing but whatever the force acting multiply by distance perpendicular to the cross section. So force acting P and distance, you can see that diagram is nothing but 200 mm. So P into 200, P is nothing but 300 Newton. So 300 multiplied by 200 is nothing but our bending moment, MB. Where next, Y is nothing but the further distance from this neutral axis. Here you can see in this diagram, this is nothing but the neutral axis. There will be a neutral axis in between. So the distance of the furthest distance from the neutral axis is nothing but up to this layer. So this is nothing but the 3t divided by 2, half of that total distance. So this is nothing but this simply y is equal to 1.5 times t. Similarly, how to find out area moment of inertia? I is nothing but b d cube by 12. As it is a rectangular cross section, the equation for the I is nothing but b d cube by 12, where b is nothing but t and d is nothing but 3t. So here the moment of inertia equation becomes t upon t multiplied by 3t bracket cube divided by 12. Then by solving or some simplifying this equation will become 40,000 divided by t cube Newton per mm square, as it is a bending stress. So this is nothing but the equation 2. You can see from equation 1 and equation 2, the unknown is nothing but t. So these two stresses, compressive stress as well as bending stress, these two stresses acting simultaneously at that component, at that cross section of xx. So we have to superimpose these two terms and we have to find out the resultant of these both the stresses, because these are acting simultaneously at a single time on this component. So how to find out? This will be in step number 3, that is calculation of dimension of cross section by superimposing both the stresses. Here you can see superimposing the two stresses and equating to the permissible stresses, right? So permissible stress we calculated in the first step is nothing but 160. So how to superimpose? So that sigma b bending stress and compressive stress are in opposite nature, because compressive stress we consider as a negative value, right? So here the superimposing of these two terms at the same cross section is nothing but bending. Here 40,000 divided by t cube is nothing but bending stress we calculated by this equation. Here you can see bending stress is 40,000 divided by t cube and compressive stress is 100 divided by t square. So by compressive stress is always negative, so it is bending stress minus compressive stress here, that is 160, that is equal to 160. 160 is what? So 160 is nothing but permissible stress that we calculated in the first step. So by equating this or by solving this equation, it becomes this quadratic equation t in the terms of t cube t, right? So for solving above equation by trial and error method, we get the value of t is nothing but 6.3 mm. So that is nothing but the thickness of the C section or thickness of the hexa frame. So let's have a look on second numerical. The problem statement for second numerical is like this. It is also the eccentric loading problem. As the load acting at having at some distance from this axis of this component, right? So let us see the example. An offset link subjected to the force of 25 kilonewton as shown in figure. Here you can see the diagram of that offset link. That link is subjected to the force 25 kilonewton. His P is nothing but 25 kilonewton. It is made of gray cast iron FG300. See, the gray cast iron, for the gray cast iron designation is nothing but FG300. 300 is nothing but that SUT value, ultimate tensile strength. As it is a ductile material, there will be a SUT value. The factor of safety is 3. To design this, factor of safety required is nothing but 3. So we have to determine the dimensions of cross section of that link. Here also we can see the dimension of cross section. It is shown by hatched line. The cross section thickness is nothing but t, and this width is nothing but 2 times t of that C link, offset link. So we have to find out these thicknesses. So how to find out? Again, let us have the given data. Given data is nothing but P is 25 kilonewton load acting. As why it is eccentric, again we can see the distance is nothing but from this neutral axis or from this fiber, the distance is nothing but 10, right? So this is nothing but the having eccentric distance. So that's why the force is nothing but eccentric force. So eccentric force is nothing but 25 kilonewton. SUT value is 300. As we discussed, the designation of gray cast iron is nothing but FG 300. It is given in the problem. So in that designation, the 300 is nothing but SUT value. SUT is nothing but ultimate tensile strength. See the ductile materials, when we design the ductile materials, component subject means having the ductile material, then SUT is nothing but design criteria, ultimate tensile strength. And if you design the brittle material, if you design the brittle material, then SUT will be the design criteria. And if you are designing the ductile material, then SYT, yield strength in tension, is nothing but design criteria. Like in previous problem, we have taken a SYT value, but here the material is nothing but brittle precast iron, that is brittle material. So SUT will be the design criteria, and the factor of safety is given to design this is nothing but 3. So let us see how to design this C or offset link. So it is again in step number 1, we have to find out the permissible tensile stress, as this cross section will be subjected to the tensile stress and bending stress. So sigma t is nothing but, here you can see the SUT value, SUT divided by factor of safety. There is a little bit change because this is nothing but the brittle material. So here 300 divided by 3, SUT is 300 and factor of safety is 3. So allowable tensile stress is nothing but 100 Newton per mm square. Then in step number 2, again we have to find out what are the different type of stresses that can be developed on that cross section if the eccentric load P is acting. So the stresses developed are nothing but direct tensile stress and bending stress. Here you can conclude that by this diagram, by observing this, the component cross section will be subjected to the tensile stress as well as bending stress. So that stresses are maximum at the top fiber. Here in the top fiber, the stresses are maximum. So we have to find out these two stresses separately. So tensile stress is nothing but simply force divided by area. Here in that equation you can see the tensile stress is nothing but force divided by area, and bending stress is nothing but mb y upon I. This is total resultant stress is there, right? So total stress acting on the component is nothing but combination or addition of tensile stress as well as bending stress. In previous numerical we minus this because that will be a compressive stress. In previous lecture there will in previous numerical there will be the compressive stress developed. So we minus that compressive stress from this bending stress, but here the tensile stress is there, as the tensile stress is having the same nature as a bending stress, so both nature is same, so both are the positive values. So bending stress plus tensile stress here in this problem. So bending stress plus tensile stress, how to find out that? Tensile stress first, P divided by area. P is given 25 kilonewton, so 25 into 10 raised to 3. Area is given, how to find out the area is nothing but T into 2T, that is rectangular cross section. So area is T into 2T. That is first term is nothing but tensile stress. Secondly, bending stress. So here mb y upon I. Bending moment, how to calculate mb? Mb is nothing but bending moment. Again you can see here bending moment is nothing but this one. So eccentric force P divided multiply by this total distance 10 plus this, up to this we have to find out the distance neutral axis about this axis, right? So this total distance, eccentric distance, is nothing but 10 plus up to half of this 2t. So here 10 plus t, that is taken here. You see here the bending moment is force 25 into 10 raised to 3 multiply by this 10 plus t is nothing but perpendicular distance. Why t is there? Because we have to take the distance up to this neutral axis, that is eccentric load. And y is nothing but half of this neutral axis, half of this total distance or total width. So total is nothing but 2t. So y distance is farthest distance from the neutral axis is nothing but t. And how to find out I? Area moment of inertia. Area moment of inertia is nothing but, for rectangular section again, bd cube by 12. So here you can see b into t cube by b into d cube by 12. So b is nothing but t value and d is nothing but 2t value. So t into 2t cube divided by 12. So here is nothing but from equation A and B. Here you can see this is permissible value is 100 and the actual stress developed is nothing but this value. So we have to equate that two equations to get the thickness value. So this is step number 3, calculation of dimension of cross section by superimposing equation A and B. Equation A is equation A is for permissible stresses, and equation B is for actual stress, bending stress, total stress acting. So by equating this, by simply it is a, in this equation T is nothing but unknown. Again we solve this quadratic equation, so that by solving this quadratic equation and trial and error method, we get the value of thickness of that offset link, that T is nothing but 25.5 mm. So that's how we can design the component subjected to the eccentric loading. Okay, thank you.